All right, we'll go ahead and get started. So this is lesson number 35 on graphing parametrics. So this is a new unit. Here's where we're at in the calendar as of now. It's crazy. We're really getting close to the end here. So we have this week is a short week. I don't know if y'all know, but Friday is no school. It's inclement weather day. And so we have I'll do Zoom office hours on Thursday. We have graphing parametrics is the intro lesson on what parametrics is today. I'm actually going to move this one here to Wednesday because they sent me an email that I need to go to the school on Tuesday. So I'm going to the school to like clean out my classroom and stuff. So that's actually during this class time. So I'm going to move that converting parametrics to Wednesday. So no class tomorrow. We'll have class on Wednesday. Okay. Then Zoom office hours on Thursday and then longer weekend. So for the Zoom office hours, by the way, the numbers have been dwindling. I don't know if that's a good thing or a bad thing. It could be good. It just means you don't have any questions. You're understanding this stuff. It could be bad. It means you don't have as much motivation to ask. Hopefully it's the former rather than latter. But we start off with several people and then a few people and then one person and then no people. So I'm pending how I'll still keep that open and I'll just log on. If no one's on in the first 10 minutes, then I'll just close it off, but just want to keep that space if you do have questions. In addition to some of y'all send me questions on Remind, but that is still available. Okay, so, and then next week we'll continue. So we'll do parametrics all the way until next Tuesday. And then we'll do our last unit, which is polars, which is a 2-day lesson. And then y'all have AP exams. And so we're just gonna do a review during that time. Okay, I haven't thought about what that looks like. Mainly just gonna focus on the topics that you will be doing immediately next year in AP Calculus first semester. Okay. All right. Well, any questions on calendar stuff or anything like that before we get started? All right. Well, we'll go ahead and get started then. We will learn math, build character, never give up, and ask why. All right, so here is a big picture of what we've done thus far this semester. Just kind of give you some insight of the big picture. So we started the whole 4 to 6 weeks is basically the unit circle. And this is going to come up one of the first things you do in AB calculus, okay? That was most of the 4 to 6 weeks. The 5th 6 weeks and the 6th 6 weeks. So this was during the 5th 6 weeks, we did law of sines and law of cosines, okay? And we did vectors, which is a whole unit. Then we did conic sections and ellipses and hyperbolas, right? That's what we just came off of doing. So right now we're here and we're talking about parametrics. That's a new unit, is not really related to the others. All of this, pretty much all of this is going to be in BC calculus material, okay? So we need to go back and review the stuff that you're going to use immediately next year. But just heads up, that's where we're at. And now we're starting a new unit, okay? So here's an example problem that we'll be able to solve by next Wednesday. So this is the end picture goal. So I'm going to read it. We won't be able to solve it yet, but just to give you a picture of how you can use parametrics. So this says a baseball player hits the ball at a 28-degree angle with an initial speed of 103 feet per second. The bat is 4 feet from the ground at the time of impact. Assuming that the ball is not caught, determine the distance traveled by the ball. So by the end of next week, we'll be able to solve this problem. There's a few components here. The question is asking, how far has a ball traveled to like this distance? How far would that be? Based on the information we have and what we know, we don't have enough information based on what we've learned in the past to solve this problem. Because we don't have an equation of the quadratic, we know the initial speed, like when it comes off of the bat, how fast it goes. We know the angle by which it is hit. And we know how high above the ground the bat is. We have to count gravity into this because that's what's pulling the ball down, right? So this would be an example of a parametric situation in which we'll solve as we work our way with the knowledge that we need to solve it, just to give you a big picture, okay? So let's talk about today's lesson specifically is just on graphing the parametrics and just an intro on what is a parametric, okay? So when you think about this problem here about the baseball, there's several components here that are taking place. You have time component. As time is passing, the ball is moving. You have the horizontal distance component, so how far the ball is traveling horizontally. And you have the vertical distance component, how high is the ball in the air. And all of those are factored in here when we're thinking through the ball. So here is a visual of just a random situation with the ball. So in the first one, it says the path of a ball travels, or sorry, the path that a ball travels when it is thrown is given by the graphs below. So we have our first graph here, which shows the vertical distance of the ball, or how high the ball is. But if you notice, on the x-axis, you have time. And on the y-axis, we have vertical distance. So this is showing you as time is passing, how high the ball is. That's all it's showing you, the relationship between the vertical distance, how high the ball is, as time is passing, okay? So for example, this is saying at 1 second, the ball is up here at 70 something meters. At 2 seconds, the ball is up here at 80-ish meters. So that's just showing you as time is passing, how high is the ball, okay? And we can see that the ball starts at a height of 40 meters in this case, okay? This is not directly related to the same values as the baseball problem. This is a separate, okay? Then we have the second type of graph, which is the horizontal distance, okay? So for this case, we have on our x-axis time and on our y-axis horizontal distance. So that's saying how much distance has the ball traveled horizontally as time is passing. So if someone was here and they were throwing the ball in the air, this graph tells you how high the ball is at different times. This graph here tells you how much distance horizontally it has traveled. It doesn't matter how high it is. So this is remaining constant. So after 1 second has passed, it's traveled 40. That's what that's saying. After 2 seconds has passed, it's traveled 80, and so on and so forth. So they're showing, one is showing the vertical height, the other is showing the horizontal distance, okay, of the ball. So what a parametric graph is when you introduce these both components together with the parameter of time in mind. So now when we're graphing horizontal distance as the x and vertical distance as the y, you're getting a picture of what the ball actually looks like visually, but with the parameter of time in consideration. So what do we mean by that? Oh, what is that? Whoa, I don't know what that does. That's cool. Sorry. Didn't know that thing was there. Let's erase that. Okay, so let's say, for example, I create a chart and I say at a time, t representing time, at a time of 0, okay, what is a vertical and what is the horizontal distance of the ball? At time of 0, before any time has passed, what is the vertical distance of the ball? And that would be 40, right? Because at time 0, the vertical distance is 40. And at time 0, before any time has passed, the horizontal distance is 0. So if we graph that on the parametric graph, the vertical is the y, so here's 40. That's 40 comma 0. Oh, no, I'm sorry. Yeah, that's 0 comma 40. I did it backwards. Right? This is backwards for x and y, sorry. So vertical distance is 40. That's what this is. Horizontal distance is 0. That's what this is. Okay? And then let's say we try 1. At t of 1, what is the vertical distance? So at t of 1, the vertical distance is right here. That is, let's call that 75, the vertical distance. And at a t of 1, the horizontal distance is 40. So if we graph that on the parametric graph, 75 would be about here for vertical, 40 would be about here. So that would be when t equals 1. This is when t equals 0. And we're talking about seconds. Okay. Then let's say at 2 seconds. At 2 seconds, the vertical distance is right here at, let's say that's 80, I'm rounding. And over here at 2 seconds, the horizontal distance is 80. So 80 for the vertical distance and 80 for the horizontal distance. So it'll be about here at t equals 2. Okay. Then we have, let's do 3. So at t of 3. At t of 3, vertical distance is at 50. Horizontal distance is at 120. So we're going to be at 50, right here, 120, somewhere right here. T equals 3. And then let's do t equals 4. After 4 seconds, the ball vertical distance is 0, so it is on the ground at that point. And horizontal distance is 160. So 160, 0, it's going to be about here, t equals 4. Okay, so when we connect those here, that's the graph. Now, let me pause real quick right there. And just from a graphing perspective, is everyone clear on what we did there, or any questions? I see thumbs up, no questions. All right. So what this is basically showing you, the parametric graph, is you are introducing a parameter of time, okay? And so this is showing you what the actual ball looks like with the relationship of the horizontal distance and the vertical distance. So this would be an accurate picture of what the ball looks like. This one would not be, because that's time as your x-axis, right? So this introduces it's kind of how you would relate 3 things: horizontal distance, vertical distance, and time. Time being the parameter here. So a parametric graph basically allows you to introduce a parameter, in this case time, versus a regular XY graph. You're looking at the relationship between 2 things, right? So a parametric graph allows you to introduce a parameter. As that parameter is changing, what is happening with those dependent and independent variables is what we're looking at, okay? So in the first example, we had vertical distance as a function of time. So here's vertical distance dependent on time. Second one, we had horizontal distance as a function of time, because horizontal distance was dependent on time. And both the horizontal and vertical distances in these first cases are dependent on time, right? In the first 2 examples. Okay. In the parametric graph, I don't have a way to bring this back because the graph erases. Let me go back real quick. So there's a way to copy and paste this. T equals 0. I'm going to do a rough sketch of it, okay? T equals 0. T equals 1 was about here. T equals 2. T equals 3. T equals 4. So that's just a rough sketch, just so I can see these notes. Okay. So this graph can tell you where the ball is positionally at any given time on the interval, okay? Because if we didn't have this parametric graph and we didn't plug in t every time, we wouldn't have this information. And if I asked you, where is the ball after 3 seconds, just from this graph, you couldn't answer that, right? If I said, where is the ball after 3 seconds, just from that graph, without the parameter of time, you wouldn't know where the ball is at that time of 3 seconds. So with the parametric graph, with introducing that parameter of time and including that as we graph, this was t0, 1, then we know we're seeing not only the horizontal and the vertical distance, but as time is increasing, where is the ball there? So t is the parameter, okay? So this particular graph is showing you the interval of time from 0 to 4, 0 and 4 included. That's the interval by which you're looking at where the ball is at the time from 0 to 4. So from 0 seconds to 4 seconds, this parametric graph is showing you what is the vertical and horizontal distance in the position of the ball, okay? Now, when you draw a parametric graph, it's important that you draw arrows. You always have arrows on a parametric graph, indicating the direction by which the object is going, or the graph is the direction in which the graph is moving. So because the time is increasing as we go to the right, your arrows will be like so. So parametric graphs will always have the arrows. The arrows would indicate which direction you're going as you're increasing on your interval, whatever your parameter is, okay? Now, last piece here for this example, a parametric equation. So this is what we're used to. We're used to rectangular equations, which come in the form y equals, and then you're relating y to x, right? This is the rectangular equation we're used to. This would be the equation of this graph here without the t, right? It's just a quadratic that's negative. This would be the equation in standard form of this particular graph here. That's what we're used to relating y and x, okay? When you introduce the parameter of time, okay? This should say a t, I'm sorry, typo. So change that to a t. When you introduce the parameter of time, then you would have what you call parametric equations, which are going to have two different equations because you have to relate y to t, and then you have to relate x to t because t is your parameter. So this first equation is going to show you the y, or the height, vertical distance, with respect to time. So when you plug in, let's say you plug in t equals 0 here. When you plug t equals 0 here, you're going to get that, you should get that y value, okay? Or if you plug in t equals 0 here, you would get wherever the x starts at, which would be this. Okay, so that's showing you so parametric equations have two equations, y with respect to x, or y with respect to t, I'm sorry, and x with respect to t. I'm going to dive more into that next class. But just remember, parametric equations are going to have two with respect to x. Rectangular, what we're used to, is one with respect to y and x, okay? So looking at this example here then, where it says sketch the graph of the parametric equation over the interval 0 to 3, because we have two equations, we have three variables, x, y, and t. That is a parametric equation. And your parameter is t. That's the interval that we have here. T is the parameter. We're finding what is the graph from 0 to 3 of these parametric equations, okay? So what we would do here to graph that is we're going to create a t-chart. So we're going to select values for t, the steps here, over the given interval. We're going to start with the lowest value. So we're going to start with the t of 0. Okay? And then we're going to find the ordered pair corresponding to each value of t. So we're going to plug in 0 for t. First in the x equation, so if we plug in 0 here, 0 minus 1 will be negative 1. So the x is negative 1 when t is 0. Then we're going to plug in 0 for the t here in the y equation. 0 squared will be 0. 0 minus 2, negative 2. So the y would be negative 2. So that means when the parameter t is 0, the x value is negative 1, the y value is negative 2. So we would plot that then on the graph. Okay, so that's at t equals 0. When t is 0, you have a point there. And we would keep going. We would do for 1, 2, and 3. And we're going to stop at 3 because it goes from 0 to 3. So if I plug in 1, this is just now the algebra here, 1 minus 1, 0. Plug in 1 for here, 1 squared 1 minus 2, negative 1. So at a t of 1, a point right here is 0, negative 1. So that's t equals 1. Okay. And then same thing with 2. We're going to plug in 2. If I plug in 2 there, 2 minus 1, 1. X is 1. Plug in 2 here. 2 squared minus 2. 2 squared would be 4. 4 minus 2, 2. So at a t of 2, you have a point of 1, 2. Notice I'm writing t equals on the graph. When you graph a parametric, you have the t equals. So you can see as the parameter is increasing, where are the points. Plug in 3. 3 minus 1, 2. Plug in 3 here. That's 9 minus 2, 7. 2, 7. T equals 3. Okay. So we have done step 1, select the values for t over this interval. We have done step 2, find the order pairs corresponding. Step 3, we plotted the points. Now we connect the points with the curve. So in this case, this one is going to curve slightly like this. We're not going to draw an arrow because it's only from 0 to 3 is our parameter. And then we're going to draw arrows to show the direction along the curve as t is increasing. So as t is increasing, it is going up. And so our arrows here. So that is graphing the graph of the parametric equations there. Okay. Now, if we notice here, that's going to be if this parameter was negative infinity to infinity, and we kept plugging in points here, what we should notice what would happen is it would end up being a quadratic. Next class we'll talk about how do you get the equation of the rectangular from this. Like how would this give you a quadratic? We'll talk about that next class. All right. Any questions thus far? I'm gonna give you one to try on your own, but I want to make sure we're good so far. So you can do this on I didn't put this one on the notes, but you can go ahead and try this one on a sheet of notebook paper or graph paper. So go ahead and try to graph this, okay? I got several of y'all done. Some of y'all might still be working, but you can check what you got so far. Claudia, could you tell me what you got for -2? Jimena, could you tell me what you got for -1? Sophia for 0, Brianna for 1, and Natalia for 2.
For X, I got 5, and for Y, I got -6.
For X, I got 2, and then for Y, -3.
For X, I got 1, and Y, I got 0.
For X, I got 2, and for Y, I got 3.
For X, I got 5, and Y, I put 6.
All right. We good with all of those values? Any of them we need to change or we disagree with? No? Okay. So then when we graph that, we should have 5, -6. As t equals, you want to write the t as you write it. T equals -1, 1, 0. T equals 0, 2, 3. T equals 1, 5, 6. T equals 2. And we draw it. Now you can know that you generally did it right if it kind of connects. Like if you have a point over here, and that's like t equals 3 or something like that, then something's off. So that looks good. And then you would write your arrows to indicate orientation. And so your orientation is going that way. So that's graphing the parametric. Very good. And next class we'll talk about writing the equation of that. That would be a parabola. We'll talk about that next. All right, one last piece. I want to make the connection here between this and what we learned last class, and we'll talk more about the equation later. But let's say we want to sketch the graph of this parametric equation. over the interval 0 to 2 pi. So now our parameter is it's an angle measurement. So a parameter doesn't have to be time. It doesn't have to be distance. It could be angle. It could be a lot of things. So in this case, it's an angle measurement. And we have trig here. So let's go ahead and create our t-chart. T, x, and y. We're going to start at 0. That's where our t, our lowest t is 0. So we're going to plug in 0 for t. So x equals 6 times cosine of 0, and y equals 4 times sine of 0. So hopefully we know our unit circle well we know what those are, right? So cosine of 0 is what?
1.
1. And then 1 times 6, that would be 6. Sine of 0 is
0.
4 times 0, that would be 0. So 6 comma 0. It's going to be for t equals 0. Very good. Now, then it goes from 0 to 2 pi, and there's an infinite amount of values between 0 and 2 pi. So we have to think about which is going to be the easiest value for us to use, the easiest angle for us to use to get a clean number to be able to graph it. So what will be the next easiest value to use to plug in for t here on the unit circle? That will give us a clean number. Ideas. Because we have an infinite amount of values from 0 to 2 pi or 0 to 360. So what could we plug in for cosine of t that would give us a clean number that we can work with?
2.
Say that again.
Pi over 2.
Yes. Why pi over 2?
Because the cosines and sines are just one number.
Yes. So we're thinking about our quadrantal angles here. If we go pi over 2, that's just 0, 1. And so that's a clean number. Anything within this range has a radical in it, right? Pi over 3, pi over 4, pi over 6, all have radicals in it. So that's not as clean. It's not going to help us to graph it on here. We could, it just be a decimal. So, okay, so cosine, so you said pi over 2. We're going to say t is pi over 2. So cosine of pi over 2 is our 0 here, right? So that's just going to be 0. Sine of pi over 2 is 1. So 4 times 1 would be 4 here. So 0, 4 is going to be for t equals pi over 2. Good. All right, then we got, what's the next one that we would want to use?
Pi.
Yeah, pi, that's going to give us a clean number. Pi, because that's negative 1 comma 0. So x equals 6 times cosine of pi. Cosine of pi is negative 1. So 6 times negative 1 should be negative 6. Would be for t of pi. And then we do the same thing for y. 4 times sine of pi. Sine of pi is 0. So 4 times 0 would be 0 there. So negative 6, 0 for t equals pi. Okay. And the next clean value to use?
Pi over 2.
3 pi over 2. Because that would be 270. And that would be 0 comma negative 1. So cosine would be 0. Sine would be negative 1. So 3 pi over 2. X equals 4 times sine of 3 pi over 2. So that's our next one we're going to use. So this is 0. So 6 times 0 will be 0. This is negative 1. 4 times negative 1 will be negative 4. So 0, negative 4 for t equals 3 pi over 2. All right, and then we can bring it full circle. The last one is to 2 pi. So if we do 2 pi, remember, is the same thing as 0 in terms of what it gives you. Like sine of 0 and sine of 2 pi is equal to the same thing. So this is going to be the same as this here, 6 comma 0, right? Because sine of 2 pi is equivalent to sine of 0. And cosine of 2 pi is equivalent to cosine of 0. So these values are going to be the same. So it's going to come back around, and over here you have t equals 2 pi. So it's in the same place as t equals 0. So our parametric is going to be like, totally missed that bottom one. Like that. And the direction by which it is going is this way. Okay. And we notice that creates, what graph is that? Hello? Okay, I see Kelly sent it in the chat. That is an ellipse, yeah. So this is kind of connecting what we talked about last week and the week before, right? So this is a conic section. So somehow this and parametrics is related to ellipses. That's crazy. Let's touch on that actually, because I think it's cool. How is a trig and the unit circle and parametrics connected to ellipses? All of which we've talked about this semester. Math is cool like that. Let's talk about that. Let me add a new slide. We're gonna talk more about this, but I just think it's fun. So we're gonna, how do I delete this one? Delete. So we have x equals 6 times cosine of t. Where is it? Where is it? And y equals 4 times sine of t. So how did that create an ellipse? Here's why. Let's say we try to solve this for t. We divide by 6. And we get cosine of t equals x over 6. And we solve this one for t, we divide by 4. We get sine of t equals y over 4. Now, what we can do, if we think about this, and this is even crazier, this connects to another lesson we learned, trig identities. If we think back to the trig identities lesson, the relationship between cosine and sine, and how that might relate to this, we kind of see the ellipse a little bit from there. I wonder if anybody can see it. This has to be, this is close to a trig identity right here, these two connected, right? So, or it's close to a ellipse equation, right? Because the ellipse equation is like this. Sorry, a squared, no, not a squared, I'm sorry. X minus h squared over a squared plus y minus k squared over b squared equals 1, right? That's the ellipse equation. Can anybody think about what trig identity would help us to get it to look like that? Based on what we have here. Think about your trig identities. Thinking back to what we talked about before conic section, trig identities. What trig identity could get us there to look like that? It's almost in the form of an ellipse. I can hear some of you ruffling for your formula sheets. Anybody? Come on, somebody knows this. We need that to look like x minus h squared over a squared plus y minus k squared over b squared. Try to make the connection equals 1. You have this. This looks similar to that. What trig identity connects cosine and sine to look like that? we have few trig identity.
Sine squared plus cosine squared equals 1?
Yes, very good.
Oh.
Yes. Thank you. Take us home. Think about this. Cosine squared of theta plus sine squared of theta equals 1, right? And so if cosine of this t here is equal to this, we can substitute this for cosine, because this is the same thing as saying cosine of theta squared, right? So we can substitute for cosine, we can substitute x over 6 squared. And if we take this, sine is equal to that, y over 4 squared, we can substitute that. There's a plus in here that equals 1, and when we simplify this, we get x squared over 36 plus y squared over 16 equals 1. And what is that? That is the equation of an ellipse. Isn't that beautiful? That's putting together a lot of things we learned. Trig identities, ellipses, parametrics, trig unit circle. Pretty cool. And if you look at this, x squared, we had x squared over 36 plus y squared over 16 equals 1. If you think about it, that is the equation of this graph, because the a of this is 6, right? And 6 squared gives you that 36. The b of this is 4, and 4 squared gives you this 16. And then the center is 0, 0, and so that's why your h is 0 and your k is 0, and that's why you don't have it there. Bringing it back full circle. Ah, pun intended. All right, beautiful. Any questions? All right. In closing, so again, we're moving the converting parametrics over here to Wednesday. Tomorrow, we won't have class. We'll talk more about equations and the relationship between the rectangle and the parametrics on Wednesday. Zoom office hours on Thursday. If you have any questions, the practice for this lesson is posted. It's due on Thursday at 4:20. Other than that, if we're good to go.